Hi everyone, my name is Prue and I'm going to present GLU-Net, Global Local Universal Network for Dense Fluent Correspondences. This is a joint work with Martin Deneliant and Radu Timofte. So we address the challenge of dense pixel-wise correspondence estimation for pairs of images. Given a pair of source and target images, our network takes as input both and outputs a 2D flow field that aligns the source image with the target. The task of finding correspondences unifies different subtasks. The first one is optical flow, where images are consecutive frames of a video. They present little motion with similar appearances, and they also have independently moving objects in occlusion. The second subtask is geometric matching. Here, images show different viewpoints of the same scene. They experience large motions and significant changes in appearance. Finally, the last one is semantic matching, where images are two instances of the same scene category or object. They show drastic shape variations as well as appearance changes. Current methods generally address one of these tasks using specialized architecture that usually fail on other tasks. Our GLU-Net is applicable to all three tasks of optical flow, geometric matching, and semantic matching. So most of the state-of-the-art approaches rely on a feature pyramid where the flow is estimated at multiple levels. And so at a particular level, it is inferred by constructing a correlation that is then passed to a decoder. And so this correlation has been shown to be a key component for the success of the correspondence network. There are two types of correlation. The first one is global. Each feature of the target feature map, such as this one, is correlated to all of the source features. The resulted scalar products are then stored in the channel dimension of the correlation. But it thus results in a channel dimension that is directly proportional to the source feature map itself. For a local correlation, each target feature is only correlated to a small neighborhood around the target location. The scalar products are also concatenated in the channel dimension. Current architecture either have one global correlation like here or multiple local ones. The global approach on the left is limited in the range of motions that it can estimate. However, because of the dimensionality of the global correlation, the network input resolution is restricted to a fixed size HLWL, which limits its accuracy. On the other hand, the local approach on the right enables a more accurate estimation of the flow, but this network is limited in the range of motion that it can estimate. We wonder, how can we achieve robustness to large displacements and accuracy for small displacements? Our first contribution is to combine the global and the local approach. It gives GLU-Net here, which has a global and two local correlations. It can handle long-range motion and is also accurate for small displacements. But this network is still constrained to this fixed input size HLWL. This leads to our second contribution. Our adaptive resolution strategy enables GLU-Net to take any image size as input while still benefiting from a global correlation. So the way it works is the original source and target images are first downsampled to this fixed size HLWL. Feature pyramids are then extracted from both sets of images. Within the LNet, there is first a global correlation to handle large motions, followed by a local correlation. The estimated flow is then upsampled to Hnet and pass through two local correlations. These refinements on original image resolution make the flow estimation very accurate. First, we look at results on the Hpatches dataset, which is a benchmark for geometric matching. So the images here are related by homographies. And so we look at the endpoint error and the PCK metrics, and we see that GLU-Net overcomes by far all others for both metrics, and particularly it is 3 times more accurate than DGC-Net for a threshold of 1 pixel. We now look at the ETH 3D dataset, which shows consecutive frames with real 3D motion. We visualize the results by varping all of the source frames on the right to the middle target frame to the left. And so for close frames, matching corresponds to optical flow, while for far away frames, the motion becomes pretty large, and then matching can be associated to geometric matching. So we first look at the results when optical flow network PVC-Net is applied to the source images. And so we see that PVC-Net cannot handle large displacements and also light artifacts. We then apply GLU-Net to the source images, and we see that it obtains much more stable results and that it is accurate for any type of displacements, small and large. On semantic matching dataset TSS, GLU-Net also obtains state-of-the-art results, and our dedicated semantic version of GLU-Net outperforms all previous approaches. Finally, GLU-Net also obtains very competitive results in the KITTI dataset. Thank you very much. Please check out our poster and our code.